Now, let's talk about the wave function of a pair of identical particles. So classically, if we consider two identical particles, they are definitely distinguishable. Right? Suppose we have two green balls, 1 and 2. They look like the same, right? They are, well, they're all green, they're all sphere, so they're the same. However, classically, you can always label one of them as 1, another as 2. And you can always follow the motion of particle 1 and particle 2. Suppose particle 1 is moving in this way and particle 2 is moving vertically. So the state of this classical system, of course, is described by the position of the first particle, position of the second particle, momentum of the first particle, and the momentum of the second particle, right? So P1 is along the negative direction of the axis. P2 is along the direction of the positive direction of the y-axis, okay? But that's one way to label them. The label 1 and 2 are completely artificial, right? Of course, you can exchange the label. Right? So you relabel this system as, say, 2, 1. Now, this state function of this classical system becomes Q2, Q1, P2, P1, right? And P1 is now along the y-axis. P2 is now along the negative direction of the x-axis, right? This is another way to label your state function. And of course, the dynamics, the actual physics of the system should be exactly the same, no matter how you label the particles, right? So the dynamic properties of the system are invariant, right? Invariant to the label of the particle, right? So quantum mechanically, quantum mechanical identical particles are indistinguishable. You have two electrons. Yes, you can label them as electron 1, electron 2. However, you cannot really distinguish electron 1 from electron 2. Okay? You think you can label them, but actually you cannot really follow an electron closely or attach a label on a particular electron. Otherwise, you will need to know the position and the momentum of this electron, right? At the same time. And you cannot do that. That's the violation of uncertainty principle. And more fundamentally, identical particles are not distinguishable. Suppose you have an electron 1 here, and we have an electron 2 here. Well, the electron 1 can be described by orbital phi A or phi 1. Electron 2 can be described by another orbital, phi B or phi 2. Now, of course, if these two electrons are far, far away from each other, you separate them to, say, 1 kilometer. Then, of course, there's no interaction between them, and you can completely ignore the second electron when you study the first electron. You can completely ignore the first electron when you study the second electron. There's no interaction. You only need to focus on your system, okay? However, when you bring these two electrons close to each other, at some point, when you study the system, you have to consider these two electrons inside the same system, okay? They can be still non-interacting. You can still ignore the interaction between the two electrons if they are pretty far from each other. However, the state of this quantum mechanical system must be described as a two-electron wave function or two-electron state function. So let's still consider non-interacting system. Okay, let's ignore the Coulomb repulsion. We know the 1 over R12 term is very tricky. So at the moment, let's ignore it. So the quantum state of the system can be described by a Hartree product, right? We have already talked about that when we talk about the central field approximation for a multi-electron atom, right? You can use a Hartree product to describe this two-particle wave function. So the system wave function is, of course, a function of R1, the location of electron 1, and R2, the location of electron 2. And this is a product of electron 1 in orbital A, electron 2 in orbital B. This is, of course, the Hartree product. Now, if you really think about this, you have labeled the two electrons as 1 and 2, respectively. So those are the labels. And they are artificial, right? You cannot really distinguish electron 1 from electron 2, right? So if we exchange the labels, of the total wave function, say you write the wave function as R1, R2. I write the wave function as R2, R1. They should be equivalent to each other, right? Because no matter how you label the electrons, the dynamical variable or the dynamical observable for this system should be the same, right? The true physics remain invariant. So that means psi R1, R2 should be equal to either you don't have any change when you do this switch of the label, or you have a minus sign in front of psi. That's a very simple situation. we're not talking about the intrinsic phase factor here. We're just talking about what happened when you have already written down a wave function. And now you exchange the label between 1 and 2. What happened? Right? You should have either positive psi R2, R1. That means there's no change at all. Or you have negative psi R2, R1. The wave function differs by a sign, but that doesn't matter because the magnitude squared of the wave function stays the same. Right? So actually, it turns out that for fermions, you will have a negative sign. Psi R1, R2 is equal to negative psi R2, R1. And for bosons, psi R1, R2 is the same as psi R2, R1. This is called antisymmetric. And this is called symmetric. Now, let's just focus on the electrons. Electrons or fermions, they have half-integer spin quantum number, and their wave functions are antisymmetric. Why is that? Because this is consistent with the Pauli exclusion principle. Two electrons cannot occupy the same state. This is actually summarized from the observations of atomic spectra. This is an experimental fact. So if psi R1, R2 is equal to psi R2, R1, since psi for the electron is antisymmetric, then that means psi R1, R2 is equal to psi R2, R1 is equal to 0, right? So the probability distribution is 0. So it is not possible for two electrons to occupy the same state. Okay? But if you have bosons, you can actually have more than one particle occupy exactly the same state. And that's also experimental observable. For instance, in order to generate a laser, you have to accumulate multiple bosons on the same state. Okay. So we say, yes, for the fermions, for the electrons, the wave function should be antisymmetric. Now, how to incorporate this antisymmetry into the Hartree product? since you can exchange the label of 1 and 2. So in your original half-wave product, you have electron 1 in orbital A, electron B in electron 2 in orbital B. Then, of course, you can now exchange the label. You let electron 2 in orbital B and electron 1 in orbital A. Electron 2 in orbital A, electron 1 in orbital B, right? You're exchanging the label. So R1, R2 becomes R2, R1. Now, you do a linear combination of these two half-wave products. In particular, because of the anti-symmetry of the overall two-particle wave function, you should use a negative sign to connect these two half-wave products. And because the total wave function is normalized, we should put 1 over square root 2 in front of this linear combination. And this is R1, R2. This is the way to incorporate the anti-symmetry into the half-wave product. 1 over square root 2 is the normalization constant. And now psi is anti-symmetric with respect to the exchange of the labels. Right? You can easily see this. Now, if we exchange the label to R2, R1, then you have 1 over square root 2 phi A R2 phi B R1 minus phi A R1 phi B R2. And this is equal to negative psi R1 R2, right? This is the way to build in the anti-symmetry in your half-wave product. So you no longer use a single term, a single product. You should use a linear combination of the products, right? And this concept can be generated to multi-electron half-wave product. So for multiple electrons, a single half-wave product would be a product of phi I or I, right? This is, suppose you have, say, 3 electrons, then you will have phi 1, well, phi A R1, phi B R2, phi C R3, right? Or you can use 1, 2, 3 to label the orbitals. 1, 2, 3. So these 3 labels are for the orbital phi. R1, R2, R3, these 3 labels are for the electrons. Now, this is, of course, one way to label the 3 electrons. Another way would be, well, R1, you put R2. For R2, you put R1. For R3, you still put R3. That's another way, right? You have multiple ways. How many ways are there? Well, you have 6 ways, right? You have 6 permutations, right? 6 possible permutations. And therefore, to build in the anti-symmetry in your total wave function, you should do a linear combination of all of these 6 products. But how to connect them? Well, you either connect 2 terms with a positive sign, or you connect 2 terms with a negative sign. But how to arrange the positive sign and negative sign? Right? This is a very important question. So this problem is actually resolved by Slater. Slater said that for a multi-electron wave function, okay, in the independent picture, okay, because the Hartree product is really for the independent picture. And this many particle wave function or many particle product form is 1 over square root n factorial, n is the number of electrons you have. 1 over square root n factorial is the normalization constant. It's just like what we have here when we have 2 electrons, we have 1 over square root 2. 2 factorial is equal to 2. If you have 3 electrons, you will have 1 over square root 3 factorial, which is equal to 1 over square root 6, because you will have 6 permutation for this product, right? And how to connect those products? Well, Slater said you simply write down a Slater determinant. So you have phi 1 R1, phi 1 R2, phi 1 Rn. So on the first row, your orbital is phi 1. And you can put 1, 2, 3, etc. as the variable for phi 1. That's the first row. The second row is all the orbitals are now phi 2. And you can put R1, R2, until Rn as the variables for phi 2. That's the second row. And for the nth row, you have phi n as the orbital. And you put R1, R2, until Rn as the variable. So you have m by n determinant. And he said, if you do the expansion of this determinant, this gives you the correct form for the n-body determinant, for the n-body wave function. This is, of course, a linear combination of the Hartree product, right? So we can see this as a description for a particular electronic configuration. What is the particular electronic configuration? The configuration is phi 1 R1, phi 2 R2, until phi n Rn. This is the configuration. And this is actually the naive Hartree product we write down, right? You put R1 in first octal, R2 in second octal, Rn in the nth octal, all right? This is the naive single product. And of course, you can have multiple permutation. And this determinant, the expansion of the determinant, will give you all the permutations, right? After all, actually, if you check your linear algebra, the definition of the determinant comes from the permutation. If you look at the diagonal element, you have phi 1 R1, phi 2 R2 until phi n Rn. And this is exactly the electronic configuration we have written down here. This is called Slater determinant. Now, let's see, what if we exchange the label? Because now we have n electrons, let's consider changing label between electron I and electron J. So your total wave function, the total n-body linear combination of the Hartree product, is Ri, Rj, right? Now we exchange the label. We label I as J. We relabel J as I. So according to the anti-symmetry property, you should have negative psi Rj Ri, right? So if we look at the Slater determinant, when we switch the label, when we change Ri to Rj and Rj to Ri, what happened? Suppose you want to change, say, R1 to R2 and R2 to R1, then what happened? What happened is actually this is equivalent to exchange, or you can say you switch the position of the first and second column, right? This is the way we change the label when you use a determinant, right? So in general, in a determinant, in a Slater determinant, suppose this column is for electron I, and this column is for electron J. Then when you change the label, what happened is you're changing the position, or you can say you're switching the position of the J's column and the I's column, right? This is what you did. And based on the basic properties of determinant, we know that these two determinants are connected by a negative sign, right? The left-hand side determinant is equal to -1 times the right-hand side determinant. This is simply the basic property of the determinant, right? So of course, using this determinantal representation gives you anti-symmetry. Okay. And the total number of product term in the expansion of the Slater determinant, which here I just simply write down SD as the abbreviation for Slater determinant, is equal to what? Is equal to n factorial, right? That's easy enough. And that's why the normalization constant is 1 over square root n factorial. Okay. If you remember the basic properties of the determinant, you will say, okay, but this way of writing the determinant, of writing the Slater determinant, is just one way to do it. If you do a transpose of this determinant, you will get exactly the same result. This is another basic property of the determinant. So you can write down equivalent Slater determinant by doing a transpose. That is to say, okay, if you write down the determinant as phi 1 R1, phi 2, phi 1 R2, phi 1 Rn, right? This is for the first row. The second row is for phi 2 R1, phi 2 R2, until phi 2 Rn. The nth row is for phi n R1, phi n R2, and phi n Rn. You can do a transpose. You can exchange column with rows, right? If you exchange columns with rows, you have phi 1 R1, phi 2 R1, until phi n R1. And the second row becomes the second column. You have phi 1 R2, phi 2 R1, phi 2 R2, until phi 2, until phi n R2, right? And the last row becomes the last column. Phi 1 Rn, phi 2 Rn, phi n Rn. Right? The right-hand side is simply a transpose of the left-hand side. Right? So for each row, you have phi 1, phi 2 to phi n. For the first row, the variable is R1. For the second row, the variable is R2. For the nth row, the variable is Rn. And these two determinants are exactly the same. So when you write down the Slater determinant, you can write down the left-hand side determinant. You can also write down the right-hand side determinant. That's your choice. Their diagonal element, the product of the diagonal element are the same, right? It's always phi 1 R1 times phi 2 R2 times until phi n Rn, right? This is also phi 1 R1, phi 2 R2 times until phi n Rn. They are equivalent. Okay. Now, after introduce the concept of spin, so spin is an intrinsic property of the particle, of the electron, right? So, of course, the electron can also move in the coordinate space, the spatial, the three-dimensional Cartesian space, right? That's the spatial motion. So really for electron, you have a sort of the so-called external motion in the space and intrinsic motion, that's spin. So really the state of a single electron should be characterized by two parts. The first part is the spatial function. The second part is the spin function, right? So now we have the concept spin orbital. The state of an electron, let's say phi for a single electron. Phi, of course, is a variable of r and s. R is just the spatial coordinate. Right? So in the three-dimensional space, it's x, y, z. In spherical coordinate, it's r, theta, phi. The spatial coordinate characterizes the location of the electron in the three-dimensional space. Right? It's the true coordinate you can see, you can visualize. Right? S is what is so-called spin coordinate. It's actually the intrinsic coordinate of the electron. You cannot visualize it, you cannot see it, but you know there is an additional degree of freedom that is related to this intrinsic motion of the electron. It's the electron spin. So this is the intrinsic coordinate. You cannot visualize it. You cannot visualize it, but it's there, right? Of course, here we use the same notation as the spin quantum number. I still use S, but this S is not the spin quantum number. This S is simply a parameter that characterizes the spin of an electron, or spin state of an electron, or the intrinsic degree of freedom of an electron. Of course, you can say, you can really use MS to characterize it, right? Because it's alpha state or it's beta state. But usually we write S, or sometimes in some textbook, people use sigma. They mean the same thing. They mean the same thing, the spin coordinate. So this phi is really the complete description of a single electron. And this is defined as the spatial part times the spin part. So psi of R is the spatial orbital. That is the spatial function of the electron. It only depends on the x, y, z, or on the external coordinate, or on the spatial coordinate of an electron. And this kept ms. Actually, it should be s ms, in which s is the spin quantum number. But for an electron, s is equal to 1/2. You don't have other values for s, so we can just ignore it. We can just drop off the s. We can just write down the ms. And this is, of course, the spin function or spin state. Okay, we simply drop s. We drop the spin quantum number because it can only be equal to 1/2 for an electron. Okay, so the spin state is written as ms. This is the case for single electron. So this set of coordinate, the spatial coordinate and spin coordinate, can be written as simply x. X is a collection of spatial coordinate and spin coordinate. And this is the complete electronic coordinate. Phi of x is called the spin orbital. So of course, for single electron, the spin orbital should satisfy the orthonormal condition. That is phi star I x phi j x dx should be equal to delta ij, right? So this actually implies, because when you do this integral, actually it contains two parts. The first part is for r, for the spatial coordinate. The second part is for spin, right? For the spin coordinate. So that implies that you actually have this inner product alpha beta is 0. Or alpha alpha beta beta is equal to 1, right? Another way to write this is if you want to explicitly write the spin coordinate, then you have alpha star spin coordinate, beta spin coordinate, d spin coordinate is equal to 0. Alpha star s, alpha s ds is equal to beta star s, beta s ds is equal to 1. Okay? Again, here, this s is really not something you can visualize. It's there. You cannot really say it's x, y, z. No, you don't have this. X, y, z is therefore the spatial coordinate. S is something intrinsic in the electron. It's there, it characterizes different spin states. It's either alpha state or beta state for a single electron, right? So this kind of notation is really a kind of abstract notation. Yes, you can write down ds and you can do the integral over ds. But what does this mean? It really means the inner product of alpha and beta for the same electron is equal to 0. In other words, alpha cat and beta bra, or alpha bra and beta cat, are orthogonal to each other. Okay. So this inner product here, including this inner product here, means the integral is over the spin coordinate. So for multi-electron system, you really have, instead of simply 1 dx, you really have dx1, dx2, dxn. You have n electron, right? And you can separate dx1 as dr1 times dx1, right? So you really have dr1, dr2 to drn times ds1, ds2 to dsn, right? And of course, again, alpha star for Si, this is for the ith electron. Alpha Si dsi is equal to beta star Si, beta Si, dsi is equal to 1. Alpha star Si, beta Si, dsi is equal to 0. Okay. So now, suppose we have a spatial orbital. And we have 2 electrons on this spatial orbital. This is equivalent to say we have 2 occupied spin orbitals. So we can draw a spin orbital. So this is the alpha spin orbital. And we have a beta spin orbital. So a doubly occupied spatial orbital is equivalent to 2 singly occupied alpha spin orbital and it's equivalent to 1 singly occupied alpha spin orbital and 1 singly occupied beta spin orbital. Okay, so alpha spin orbital, of course, is psi 1, which psi represent the spatial distribution times alpha 1. Beta spin orbital is, of course, psi prime 2, beta 2. Now, here I use psi prime. This is because psi 1 is not necessarily equal to psi 2. That is to say, when you really describe the system with the language of spin orbital, so even though you draw a pair of electrons occupy the same orbital, it doesn't necessarily mean that the spatial part, the spatial function of the alpha electron is equal to the spatial function of the beta electron. If psi 1 is equal to psi prime 2, that is consistent with our conventional thinking about 2 electrons occupy the same spatial orbital, right? So this is really the conventional thinking. About 2 electrons occupy the same spatial orbital. Right? This is the concept that we have since freshman general chemistry, right? This is what we have. This actually is called the restricted formalism. The corresponding Slater determinant is called the restricted Slater determinant. But they don't have to be the same. Actually, if you do a variational treatment, right, you're minimizing the system energy with respect to the shape of your spatial wave function, of your spatial orbital. Then, actually, in a lot of cases, psi 1 is not necessarily equal to psi 2. Unless you say, I put a constraint on the variational treatment, and I simply let, or I force psi 1 is equal to psi 2 for a pair of electrons occupy the same orbital. Then if you do this, then of course, you always do restricted Slater determinant. But sometimes we don't do that. We allow psi 1 being not equal to psi 2. Okay? So this is the so-called unrestricted Slater determinant. The corresponding Slater determinant is called the unrestricted Slater determinant. And usually, this unrestricted formalism will give you lower energy. We haven't talked about how to actually variationally optimize the shape of the spatial function. But here I just give you a concept. Okay, we can do that, and we will do that in the future when we talk about Hartree-Fock theory. Now, another quantity that we actually usually talk about this is the so-called occupation number. occupation number for a spatial orbital could be 0, 1, or 2. When the occupation number is 0, that means there's no electron on this orbital. So it's an empty orbital. When the occupation number is equal to 1, you can say this orbital is singly occupied. When the orbital occupation number is equal to 2, you say this orbital is doubly occupied. And the maximum number, the maximum occupation number for a spatial orbital is 2. You cannot have more than 2 electrons occupy the same spatial orbital. This is forbidden by Pauli exclusion principle. If you talk about the occupation number for a spin orbital, you can have 0 and 1. It could be empty, it could be occupied by single electron, okay? You cannot have 2 electrons occupy the same spin orbital, because that means these 2 electrons have the same spin state at the same spatial point. That's again forbidden by the Pauli exclusion principle. At the same point, you can only have 1 electron with, when I say at the same point, I'm talking about the X space, okay? The complete electronic coordinate space, which include the spatial coordinate and the spin coordinate, okay? So if you are only looking at the spatial coordinate, that simply means at the same point in the space, you cannot have 2 electrons with same spin. Okay, so same for, so 2 alpha electrons cannot be at the same point in space. 2 beta electrons cannot be at the same point in a space. Okay. So then our Hartree product of course, when we consider spin, the Hartree product also includes spin. That's phi 1 x1, phi 2 x2 to phi n xn. You simply replace R1, R2, Rn with x1, x2, xn. That's it, right? You use the complete electronic coordinate to describe the state. I should say to describe the position of the electron and the spin state of the electron, right? And the Slater determinant for a particular electronic configuration so phi 1 x1, phi 2 x2, phi n xn. Here we're talking about a particular electronic configuration with a set of spin orbitals. This is simply 1 over square root in factorial phi 1 x1, phi 1 x2, phi 1 xn, phi 2 x1, phi 2 x2, phi 2 xn, phi n x1, phi n x2, phi n xn. Again, if you look at the diagonal element, so you have phi 1 x1, phi 2 x2 to phi n xn, and this is consistent with the notation of our electronic configuration.